We've already seen what Markov chains are, and we've seen how they can be useful in the context of algorithms. In particular, we saw how they were useful in analyzing a very simple randomized algorithm for the two-SAT problem. In general, Markov chains are interesting because they help us understand how to explore a maze um, using simple probabilistic rules. And that's what's appealing about them. And in this sense, a Markov chain is pleasing if it gives you a way to explore the entire maze. The word for it usually is the entire state space. And it's a very natural way to explore it, and it's somehow very appealing, and it turns out to be very, very useful. But it's not just about exploring, because if it's just exploring the classic depth first search, breadth first search, these do a perfectly fine job as well if you think of the maze as a graph. But there's but there's something more to it. Markov chains have this uh, ability to explore the graph in a variety of ways, and it's not just about exploring, but how you explore that makes it kind of exciting. And so, in this sense, we're interested in Markov chains that explore the maze, but not in some rigid fashion, but in some sort of a natural way, and kind of not falling into patterns, but exploring the state space in a variety of ways. So that's what's very appealing about Markov chains, and the rules that drive them are simple probabilistic transition rules. So it's very appealing. And in order with this sort of uh, a philosophy behind which these Markov chains are designed, let's try to understand them a little bit more carefully. And for that purpose, we're going to understand how the states are classified. And when you classify the states, you're also going to classify Markov chains, and you're going to bring out some properties that make some Markov chains more interesting than others. And at this point in our exploration, we're kind of thinking of Markov chains as being interesting, appealing, so on and so forth. Eventually, we will also get to a point where these Markov chains are not just interesting from a hypothetical standpoint, but also useful in some concrete context. Okay. One thing to bear with is that we are going to go through a series of definitions, but keep this philosophy of Markov chains at the back of your mind, so that these are not just a sequence of definitions, but there is some method to this madness, some underlying perspective that guides us in setting up these definitions the way they are. Okay, so uh, so just to remind ourselves, we are interested in time homogeneous discrete space, discrete time Markov chains. So during this lecture, when we talk about a Markov chain, this is the type of Markov chain that we are referring to, and sometimes we'll just shorten it to MC. Okay, and also to remind ourselves, a Markov chain can be represented as a graph in which the nodes are the states of the Markov chain, and the edges are directed and positively weighted, and those positive weights can be thought of as probabilities. So if you add up the weights of the edges going out of a state, it has to be 1. Okay, and just to be clear, sometimes you may not have any outgoing edge explicitly mentioned, and those states are called absorbing states. And essentially, once the Markov chain reaches such a state, it's never going to leave that state. So one way to think of it is these are states that have a self loop where the out edge, the self loop can be thought of as the out edge with probability 1. Okay. And throughout this discussion, we're going to go back and forth between the classic Markov chain terminology and the graph theoretic terminology. And for many of us, including myself, the graph theoretic terminology comes quite a bit more naturally than the Markov chain terminology, but they're fairly intertwined with each other. And so, from the point of view of gaining a better intuition about what is going on, it's better to keep to relate Markov chains and graph theory, the underlying graph theoretic perspective, and keep going back and forth so that it reinforces our intuition. Two states I and j are said to communicate with each other if they're both reachable from the other. This is a Markov chain definition, but there's a very easy and clear way to understand this from the perspective of graph theory. So remember the graph that represents the Markov chain? Well, those two states that can communicate with each other are essentially two nodes such that there is a path from node, say, I to node j, and also there is another path from node j to node I. So this is what we mean by two communicating states in a Markov chain. Essentially, they're connected in the underlying graph representation. With our goal of understanding Markov chains as tools to explore a space of states, let's ask a question. When are we guaranteed to be able to explore all the states? Since the graph is directed, it's easy to construct Markov chains such that some states simply don't get explored, depending on where you start and so on and so forth. So, those Markov chains, in some sense, are well, at least less interesting because you kind of miss parts of the graph. So this leads us to the definition of an irreducible Markov chain as one in which every pair of states can communicate with each other, and this corresponds to a graph that is strongly connected. So if from any state you can reach another state and vice versa. So it's an irreducible Markov chain, simply a Markov chain whose underlying graph representation is strongly connected. So let's ask our second question, just to give some importance to Markov chains that are not irreducible. If an MC is not irreducible, which states will be visited repeatedly? In other words, are there some states that will be visited once, maybe once or twice, and then you somehow stop visiting them? Is that a possibility? Well, of course, yes. If you have a directed graph, so let's make ourselves an example here. You'll have to make up the transition probabilities, but well, let's see, something like this. If you start at either state A or state B, you might be going back and forth a little bit, but once you go to state C, well, C is an absorbing state, and there is no hope of coming back to A or B. So let's explore this idea a little bit further. Let's consider a Markov chain in some state I. We're going to call that state I a recurrent state if the probability that the Markov chain will return to I eventually is 1. So in this simple example, once you go from A to C, then there is no hope of returning back to A. So if you are at state A, there is a certain probability with which you will never return back to A. So then A is not a recurrent state. However, C is a recurrent state, because if you are at C, eventually you're going to come back to C. In this case, in fact, you'll be at C at every time step, but you can design more interesting Markov chains where you can come up with states so that you keep on returning back to them. Those are called returning states, recurrent states. Otherwise, they're called transient states because, well, the Markov chain may go through it, but it may not. It may go into another part of the Markov chain from where it will never return back to it, and so such states are called transient. So in this case, A and B are called are transient states. So from a graph theory point of view, the question is what states are recurrent and what states are transient. Think about this a little bit carefully. You may want to pause for a little while and answer this question to your satisfaction, because this will ensure that your intuition is going in the right direction. Okay, so the question is clear. If you're given a graph theoretic representation of a Markov chain, how do you figure out which states are recurrent and which states are transient? Let's use the notation h I comma j to denote the expected time to reach state j starting at state I. Okay. So the question to ponder is, suppose you're at state I, how long does it take for you to get back to I? Remember, we're talking about recurrent states. How long does it take for you to get back? And and what is it on expectation? So that's this HII. Can this HII be less than infinite? Of course, that's quite possible. In such cases, those recurrent states are called positive recurrent. Interestingly, there are also examples where a state is recurrent, but it's not positively recurrent, meaning the HII is actually infinite. So you may want to pause and think about when such a situation might arise. And such states are called null recurrent. So when HII is strictly less than infinity, then the state I is called positive recurrent. So your task is to describe a Markov chain that has a null recurrent state. So this might require you to think about a little bit. Okay. And one more exercise. Consider a finite Markov chain. Now prove that this finite Markov chain has at least one recurrent state, and prove that all the recurrent states are actually positive recurrent. So in other words, a finite state Markov chain cannot have null recurrent states. So this actually works. This exercise works as a clue to answering the previous question. Recall that we are not just interested in how many what states can be explored and what states are not explored. We're also interested in in ensuring that the Markov chain has interesting ways of exploring the state space. And in this sense, we want to avoid some rigid patterns, and we are interested in Markov chains that have a nice fluid way of exploring all the states. So from this point of view, we're going to study a notion called periodicity. A state J is said to be periodic if there exists a period delta, which is an integer strictly larger than 1, such that if the probability, given that you were at j at time t, that you would be at j again at time t plus s is greater than 0, then this s is divisible by delta. So let's see if we can get a picture. So we're talking about a state j, okay, and we are at state j at some time t, and we're considering all future possible revisits of j, and those are at time say t plus s. And the only way you can have this probability of returning to j at some time t plus s is greater than 0 is that this s is divisible by delta. In other words, if you think of the timeline starting from t, the only possible points in time that you are likely to visit the state j again are all multiples of delta. And this kind of, if you pause and make sure you understand the definition, you realize that there is some rigid pattern by which you are revisiting the state state j. And so then the state j would be called a periodic state. If such rigid patterns are avoided, then the state j is called aperiodic. And a Markov chain is periodic if any state is periodic. So the moment you have one state that's periodic, then the whole Markov chain is said to be periodic. Okay. Otherwise, we call the Markov chain an aperiodic Markov chain. So let's do a couple of exercises. First, design a Markov chain that has periodic as well as aperiodic states. Okay. So think about it carefully and come up with a Markov chain, basically a directed graph with appropriate weights, such that some states are periodic while others are aperiodic. Okay. And another question. Consider an irreducible Markov chain. Basically, this is a strongly connected graph. Can such an irreducible Markov chain have a mix of both periodic and aperiodic states? So think about it and make a claim and prove your answer. Okay. So remember, we are interested in recurrent states because, well, the Markov chain is likely to keep visiting them over and over again, but we don't want them to be visited in some rigid fashion. And such states that are aperiodic but positive recurrent are called ergodic states. And if all states in a Markov chain are ergodic, then the Markov chain itself is called ergodic. So here's an exercise for you. Prove that a Markov chain that is finite, irreducible, and aperiodic is an ergodic Markov chain. If you think about it, you've actually already proved it in a previous exercise. So that will be the clue. And with that, we end this segment on the classification of states in a Markov